Hello and welcome back. This is part 5 of a series covering the official tutorial on the Hare programming language, and this section is going to cover the section on memory management. And if you would like to stick around until the end, I'm going to give a brief update on the book that I'm writing called Programming in Hare, and so I'll let you know how that's going. So let's go ahead and jump right in. You should be on this little subsection called stack allocation and pass by reference. So this sample demonstrates the use of pointers in stack allocation, the later of which is an important design pattern in Hare. First, it passes the copy of the I variable to the increment function by reference, allowing the increment function to modify I from outside of main by using the dereference operator. Now, if you're coming from C, this is going to be pretty basic and straightforward. So here's the increment function. We'll jump over into the text editor in a moment, and it takes a pointer, and this is where we're dereferencing it. And here's the increment function where we're passing it in by reference. So when you call a function in Hare, or when the runtime calls main for you, a small block of memory called a stack frame is allocated to store all of the function's variables and parameters. This is automatically cleaned up when you return from the function, which makes it useful for getting rid of resources when you're done using them. However, it's important not to allow a reference to any stack allocated variables to persist after the function ends. Additionally, there is a limited amount of stack space, so it's often wise to seek alternative strategies when allocating large objects, which we'll address momentarily. So that would be where it says, this last sentence here, that's talking about alloc and allocating memory dynamically, which if you're coming from C is going to be alloc or calloc. I know some people say that differently. Now here where it's talking about is saying, however, it's important not to allow a reference to any stack allocated variables to persist after the function ends. So what that would be, it's called a dangling reference. And say you create an object in a function, like here, and you return a reference to it, right, like through a pointer. Well, once this function returns, it's going to be popped off of the stack, and anything inside of this function is going to, for simplicity's sake, there are exceptions. Any local variables that you created in this function are going to no longer exist. So if you have a reference to one, if you're pointing to one, that is going to be invalid, and that's called a dangling reference. So let's go ahead and cover just this first part right here, and then we'll look at the applied usage example. So let's go ahead and jump over into the text editor. Okay, so here is just an example of the basics of pointers in Hare. And again, if you're coming from C, this is going to be very straightforward. So let's step through this. We're creating a variable, a mutable variable with let, and just making it an integer. And we're printing its value here. Well, we're passing it into the increment function by reference. This is how you take the reference of an object. And because increment takes a pointer, an integer pointer, you can pass it in by reference. If you wanted to create a pointer to this object here, a pointer to I, and pass the pointer in, you could do that also. Here we're dereferencing the pointer and incrementing it by 1. And if you're not aware, this is the same as, so we're saying pointer equals the value of pointer plus 1. Well, this R value is going to be evaluated first. So this gets evaluated, and then it gets put into your pointer variable. So it's saying whatever the value is plus 1. Well, what this is just like saying this right here. There's no difference, okay? So what this is called pass by reference. So let's look at what happens when we run this program. And you can see it prints 10 and then 11. So let's go ahead and look at this real quick. And say we created a function called value. The name of it is not necessarily important. And it takes an integer, returns void, and say we did the same thing. So we're going to increment it by 1. Now let's go ahead and call that right here. We'll call value and pass in I. Okay, and then we're going to print it. And what's actually going to happen here is this function is going to make a local copy of this value, and when this prints out to the screen, I is still going to retain its original value, because this value, once this function returns, is no longer a valid object. So what's going to happen here, it's going to print 10, 10, and then 11. So let's go ahead and run this. And you can see it printed 10, 10, and 11. So what that means is, and of course there are different exceptions when you're passing, like C when you're passing an array and things like that. But generally, when you pass a value to, when you pass an object to a function, generally, there are exceptions, it's going to make a local copy of that object. And again, once the function returns, this object is no longer going to be valid. So if we were to return a pointer to this object here, and then try and use it somewhere in our main function, after this function returns, that's what would be what's called a dangling reference. So this is just the basics of pointers. Hopefully that's pretty straightforward. And let's go ahead and move on to this next little bit of code. Okay, so we're going to start from right here and look at this example of applied usage. As a practical demonstration of stack allocation, this sample also computes and prints the SHA-256 hash of its source code. A common pattern in Hare is for a constructor like SHA-256 to return an object to the stack, which you can then pass into other functions by reference using this operator. This is convenient for many objects, which can be cleaned up by simply discarding their state on the stack, but other kinds of objects, such as file handles, require additional steps. So this is what it's referring to, the applied usage. So it gave us a basic example of passing an object in by reference to a function. And now we're going to look at this example here. So let's go ahead and jump over in the text editor and step through this little program. Okay, so here we are in our text editor, and let's go ahead and cover what's happening here. So we are creating a hash and opening the main file, and what we're doing is we're hashing the source code of main.ha, putting it in a buffer, and then printing it to standard out. So let's go ahead and run this and see what happens. Okay, and you can see that it printed the SHA-256 hash of the source code of main.ha. So if I run just the standard Linux utility, SHA-256 sum on our main file, you can see that it's exactly the same as what our Hare program just did. And what that is, that's the cryptography library in Hare doing its magic and calculating the checksum of our source code. Okay, now I would like to say I am not an expert on cryptography, but we can dig into this example just a little bit to kind of understand kind of the workflow in Hare and kind of how you look functions up with HareDoc. So let's go ahead and I'll clear my screen, and then let's go ahead and jump back into this example, and we'll start with just the first function. So you can see from our import statements, this is a top-level module, and this is a submodule. Okay, so when you want to import the submodule, you have to include the top level and then the submodule. And when you call a function inside the submodule, you prefix it with the submodule name. Okay, so here we're calling SHA-256, which its full path is crypto, so cryptography, SHA-256, and then the function. So let's go ahead and look that up with Hare. So you need the full path. Anytime you're looking up documentation with Hare, you need the full path to the object, or the function, or the type, or whatever it is that you are looking up. So you can see it creates a hash, which computes a SHA-256 hash. This function is used to hash. If this function is used to hash sensitive information, the caller should call hash close to erase sensitive data. So it says we're not hashing sensitive information, so that's optional. Okay. So let's look really quick and see what a hash is. Okay. The general purpose interface for a hashing function. Now you can see that under the hood it's a struct, and we don't really have to worry about any of this. That's the great thing about abstractions. But I'm a very kind of curious person, and I'm still learning about programming, especially systems level, so I like to kind of dig into all this stuff. And again, I'm just trying to show you kind of the general workflow that you'll use for developing Hare programs. Okay, so let's go ahead and jump back over. So we're constructing a hash, and then we're opening main.ha. We've already used OSOpen before, and what's happening here, we're copying the hash of our file. Okay, so let's go ahead, we're placing it into our constructor here. Okay, so we're passing this in by reference. This is what this little program is trying to highlight here. So let's look at IO copy. Okay, you can see it copies data from one handle into another. And here's the source, here's the destination. So we're copying the source code data into our hash. Okay? Now, what we're doing here is we are creating a buffer. Now, if you want, I'm not going to get too deep into this. I'll leave some things for you to do. If you want to look this up, this is defined in the SHA-256 submodule, and this is basically a def. It's defined with def, so it's a compile time constant, and it's size 32. And this is just the size of a hash. And we are initializing it here with array initializer syntax. Let's look up hash sum and see what that's doing. And you can see it populates a user-provided buffer with the current sum. So it takes a reference to a hash, right? This is a pointer, and then it also takes a slice of bytes. Okay. So that's right here. We're passing this in by reference, and that's what this little program is trying to show us. Now here for hex encode, let's go ahead and look up this function. You can see we're importing the encoding module, and hex is a submodule. So when we look up this function, we have to use the full path. Okay? So it's an encoding, hex encode, And you can see it encodes a byte slice of a hexadecimal string and writes it to a handle, an IO handle. So we're passing in our buffer that we allocated, and we populated it, you see, with hash sum. We populated it with our hash, and we're passing in the IO handle is standard output. And then this print line function here at the end is just extra. It's not really doing anything, it's just creating some extra space. Okay, so that is exactly what is happening here in this program. Now, just for curiosity, let's kind of think about something else we could do real quick with this, right? Say we wanted to, instead of placing our checksum, instead of writing it to standard output, what if we wanted to put that in a file? Okay, well, if you recall from a previous example when we used OS open, let's look at that. So we're using OS open our main file. Now generally in C, you use fopen to also create files. So let's look up OS open, and you can see it opens a file, but it says, now here's the default flag, it's read-only. Now you see it says the create flag isn't very useful with this function since the new file's mode is set to 0. For this use case, use create instead. So let's look up OS create so that we can create a file that we'll put our checksum into. So you see it creates a new file with the given mode if it doesn't already exist and opens it for writing. So here's the function. It takes a path to a file, which is a string. It has a mode, which you can see the type is fs mode, and here are the default flags that are set. Now my understanding of this, please correct me in the comments if I'm wrong, is my understanding is that if the file does not exist, it's opened in write-only mode, but if it does exist, then it's going to truncate the data. And if you're not familiar with file truncation, basically what that means is that it zeroes out the data so that you can have a clean write to that file. So this is passed in by default. We don't have to specify this argument when we're calling this function. And you can see it does on success it returns an IO file, on error it returns an error. So we do have to handle an error. So let's go ahead and look up what fs mode is. Okay, and you can see file mode information. Now, if we look back up at OS open, you can see that when it's saying this isn't very useful with this function, the create flag, since the new files mode is set to 0. Okay, what does that mean? That's right here. It means unknown, entry of an unknown type. So what we want to use, let's give our user read and write permissions. So that's going to be the user RW flag. So let's go ahead and jump back into our editor, and let's create the function call right here, and we'll call this out file. And so let's call OS create. Now here's where we put in a flag. This is where, the path. So whatever file you would like to create to place the checksum into is going to go right here. So we'll just call it hash.txt. Now here is where the file mode goes. So we're going to use read and write permissions for our user. So you need the full path to it. fs mode user rw. And then we need to handle an error. We haven't got into error handling yet, so let's just put the error assertion operator. Now we need to import the fs module because we're using this submodule fs mode. Okay, so that's going to create the file. Now in order to actually put the contents of our checksum in this file, we want to put our out file when it encodes it into a hexadecimal, we're going to actually put that in our out file right here. Okay, sorry about that. So now when we call hex encode, the handle that we are going to pass in is our out file. So we've replaced the standard output. So instead of printing our checksum to the standard output console, we're going to print it to this file. So let's go ahead and run this program. And let me list the files. And you can see hash.txt. Now if I cat this file, here's the checksum. Okay, now if I run the standard Linux utility on the main file again, you can see it's the exact same. So that's just, I wanted to just show you a, kind of a little example of, you know, kind of the Hare workflow, looking up these functions and getting a little curious with the language and just trying some different things out. So let's go ahead and move on to the next example. Okay, so dynamic memory allocation and defer. Go ahead and place this into your text editor. So another allocation strategy in Hare is heap or dynamic allocation of resources. A simple sample program is provided here, which opens the file referred to by its first command line argument, reads up to 64 kibibytes from it, and writes it to the standard output. You can run it on itself like so. And so here we're passing in the main file itself, and that would be right here, osargs. Let's deal with the first basic example, and then we'll get into the applied example. So to allocate an object on the heap, use the alloc keyword along with an initializer in parentheses. The runtime will request the necessary memory from the operating system, initialize it to the value you provide here, and return a pointer to this value. The first FMT call in this example prints the location or address of the allocated memory, and the second call prints the value which was placed there. So it's referring to this right here. So here we're printing the address of our pointer, and here we're dereferencing the pointer. If you're coming from C, this is going to be hopefully pretty straightforward. Even though uses of alloc look like function calls, alloc is not a function and does not work like one. Among the special things it does is automatic size calculation. So it says when allocating a slice of 4 ints, you should write this syntax, not this syntax. Unlike stack allocated resources, which clean themselves up when the function exits, heap allocated resources must be freed by the caller using the free keyword. Another concept shown here is the use of defer to defer the execution of an expression to the end of the current scope. This gives you the ability to write the code which cleans up an object right next to the code which creates that object. So it's referring to this right here. We are closing this file handle right here, and we're using the defer keyword here to deallocate this buffer. There are other kinds of resources that have to be cleaned up when you're done using them, such as open files. Defer is useful for these cases too, and in this code sample, we use it to call IOClose to clean up the file opened by OSOpen. Okay, note, failing to free allocated memory causes a memory leak, which is a bug in your program. Failing to close files is another kind of leak. Several of the earlier examples have memory leaks. Can you identify and fix them? Now, I'm not going to do that. I think this series is already going to be lengthy enough. If you'd like to go back through some of the previous examples, use Hare and open up those functions, and it will tell you which functions allocate memory. So let's go ahead and jump over into the text editor and look at this first example. Okay, so here we are in the text editor, and let's go ahead and step through this program. This is just the basics of using alloc. So we're creating a mutable variable and annotating the type with an explicit type annotation. This is an int pointer. And here's our call to alloc. Remember, this is not a function. It performs automatic size calculation. Now, this might be a little different, if you're used to malloc and C, because here we're putting in a value. This is just an actual value. So alloc calculates the size automatically. We don't have to allocate a certain size and then initialize that. Here we are printing the address, and here we are dereferencing the pointer to get this value. And here is the free keyword, just like in C, to free our dynamically allocated portion of memory. So let's go ahead and run this program. And you can see it prints the address in hexadecimal, which is standard for Unix. And here is the value that we got by dereferencing our pointer, which is 42, which we all know is the answer to life, the universe, and everything. So hopefully that's pretty straightforward, and let's go ahead and move on to the applied example. Okay, so here is the applied example. Now what we're doing is we are passing in, this is an argument flag. Normally in C, you would see that up here in the main function as char star argv array or char star star argv, and that's how you pass in your command line arguments. Here we can get them with the osargs function. So by default, generally the first argument passed to your program implicitly is the name of the program itself. So we're actually getting the second argument here. Okay, now we're using, this is what it's trying to highlight here, is the defer keyword. We're closing this file. Normally you'd close it down here after you're finished with it. Well, we're using the defer keyword to close this file. Now here we're allocating a buffer dynamically. This is also what we're concerned with here. We're allocating this buffer dynamically. You can see that in this instance, we have to use an explicit type annotation to tell alloc the size of our buffer. Okay. Now there are three forms of the alloc expression. There are three forms that you can use that are documented in the language specification. I break those down in my book. But let's just step through this program. Okay, so we're allocating a buffer dynamically. Now this is 64. If I look at it again, I think it's 64 kibibytes. Yes, it's 64 kibibytes. And if you are not familiar with the difference between a kibibyte and a kilobyte equals 1024 kilobytes. So here we're deferring the freeing of this buffer to the end of the scope. And we're just writing to standard output. So what's going to happen is whatever command line argument we pass in here, it's going to read up to 64 kibibytes of data and print that to the standard output. So let's go ahead and run this program. And that's us that's us running the program. So now we have to pass in the argument. And you can see it printed out the contents of our file. So that is the basics of using alloc. I've written a brief little program. Let's go ahead and look at that, and I'm going to show you some more uses of alloc. Say, for example, you wanted to allocate some structs, things of that nature. Let's go ahead and look at that program real quick. Okay, so here is a brief little program just demonstrating some other use cases of alloc and how you would go about using it. Because at the moment the language spec is really the only tool to understand how to properly use alloc. Again, there's three different forms of it. So let's step through this. We are creating a struct, and say for example we're like making a video game. So this is a character struct with a couple of fields. Okay, now here in this call to alloc we're using type inference and initialization syntax. So we're not explicitly annotating a type. Here we're calling alloc, we're allocating a character. So this is the character struct, and we're initializing it with all of the default values here. Okay, so these are going to have default values. I do have a section in my book on default values. And then here you would have to initialize your values and then do something with them. So again, this is type inference, and this is what we could call struct initialization syntax, where because all of your values have to be initialized at the point of creation. So all of these values have to be initialized. This will default initialize them, just like with an array. Okay, now we're using the defer keyword here to free this resource when it goes out of scope. Now here I am explicitly annotating the type, so it's going to return a pointer to a character struct. And this, I guess what we could call this in-place initialization. So this is what it would look like to allocate a struct dynamically, and instead of using the default initialization, we're actually plugging in values for our fields. So for the name field, lives, health, and distance traveled. And I have just a couple of little functions here just to kind of play around with this program. So here's a hit function. Say you take damage. It takes a pointer to a character struct, and we're taking 10 away from our health. Here's an increment travel function. We're passing in a pointer to a character struct, and we are just incrementing our travel by 0.1. So obviously, something like this would be in these would be in another file, and this would be inside of a game loop, right? So this would be running at something like 60 frames per second. So I just call it here. I'm calling it twice on our Sonic struct here that we created dynamically. And then we're also taking damage once, and so we're printing out the distance traveled, and then we're printing out our health, and then I'm freeing this struct. So let's go ahead and run this program. Okay, so see, distance traveled 0.2, and our health is now 90 because we took damage. So that is the way to allocate structs. I do get into all of the forms of the three different forms, the ways. I have an entire chapter on memory in my book. It's not finished yet, but I plan to break the alloc call down in detail so that you can understand kind of the nuances of it, because if you're coming from C, it might be a little confusing, and that's understandable. So hopefully that makes sense, and let's go ahead and move on to the next part. Okay, so you should be on this section here, which is static allocation. Okay, so the third major approach to allocation in Hare is static allocation. This approach involves creating a single object, a singleton, for the whole program to use. So that would mainly be right here. Let's deal with example A and B, then we will look at the applied usage. This never has to be cleaned up because it never goes away. The most apparent drawback of this approach is that you have to allocate all static resources in advance when you write your program, and cannot allocate more or fewer static resources at runtime as needs demand them. So that's obviously different than alloc, where you can dynamically allocate resources during runtime. This can increase the footprint of your program on RAM and on disk in some cases, and there are special constraints imposed on the initializers for static variables. There are two ways to use static allocation in Hare: static locals and static globals. The first kind demonstrated in our example is a static global, which is defined using const or let in a similar manner to local variables, local here meaning local to a function. So this would be a static variable local to a function right here in the increment function. If we declare them with let, we can modify them. A static local is also declared with const or let with the addition of the static keyword. So note that after being initially set to 41, so it's referring to the increment function here, the value of x remains consistent across repeated calls to increment. Unlike a stack allocated local, which is just, if you were to remove the static keyword, it's just a stack allocated local to the function, which is allocated space in that specific function called stack frame. Stack locals are allocated to the function itself. And we will cover this practical example in a moment. Let's kind of go over what it's talking about. So, as a static resource is, again, like it says, you have to allocate it all initially, and it's not dynamic. You have to allocate just what you need. So this is a global. It's outside of main, and by default this would be static. Okay, and in our increment function, here we're creating a static local to our increment function. Now the thing about when you use the static keyword, this is going to retain, let's just say it's going to retain its memory, okay? So this is not a value that's going to be discarded when the function returns. If you call this function, you see it's incrementing it here, so when it returns it's going to be 42. Well, when we print this out, you can see that it keeps on going up because it retains its value because it is a static variable. So let's go ahead and jump over into the text editor. Okay, so I've broken this program down into, let's look at examples A and B, and then we will look at the applied usage. So for our first, this is a static global. By default, global values are static. Okay, so here what's happening, we are printing our items, and you can see in the print items function here, we don't have to pass anything in. You see we're calling the items of this array here in our printline function, and this function is aware of this value because it's a global object. Okay, so we're not passing anything in here. And then we are swapping these values here. So this is the fourth index, and this is the first index. So we're just swapping these values, 1 and 7, for our statically allocated global. And again, globals by default are static. And here, for our increment function, all of the logic is contained within the function itself. So we're creating a static local here to be a value 41. We're incrementing it and then returning that. Okay, so we're going to print this 3 times, and let's see what happens when we run this program. And you can see this is the array. So we swapped these values, and you see 42, 43, 44. So let's look at that again real quick. So you can see when we create a static local static value that it retains its memory. You can say it retains its memory. It retains that value across repeated function calls. Now, static data is placed inside of a special part of our file, generally the data segment of our file, of what's called an ELF. So your files, if you're not familiar with this, is generally in the form of ELF, which is executable and linkable format. So there are some exceptions, but generally, to not overcomplicate the issue, your static variables, especially in Hare, every value has to be initialized by default. So those are going to be placed in your data segment of your binary when you compile your program. And if you're not familiar with that, let me clear my screen and let's go ahead and build this program. Okay, we'll call it main. Okay, so let me list my files, and you can see here's the executable right here. Okay, it's just named main. Now you can use the file utility. You can say file and just pass in your binary. Okay, and it's going to give you the information on that. So it's an ELF, executable and linkable format. This just means least significant bit. It's an executable. Here's the architecture and the ABI. So it's statically linked, and so that means that it's not calling any libraries dynamically at runtime. Okay, now we can also use the readelf utility, and I'll pass in the header flag, and this gives us the elf header. Okay, I don't want to overcomplicate this example. If you're going to get into systems level programming, this is just a necessary thing that you're going to eventually have to learn about. But I wanted to show you that these are ELF files, and the point that I'm trying to make is that your statically allocated objects are placed in a special portion of this file. It's generally your data segment. Okay, so hopefully that's understandable. Let's move on to the applied example of static allocation. Okay, so now let's cover example C, applied static allocation. A practical example of static allocation is shown in the third part of this program, which, like the previous example, reads up to 64 kibibytes from the file specified by the first command line argument and writes it to standard out. In this case, however, instead of dynamically allocating a 64 kibibyte buffer, we statically allocate the buffer. We do not have to clean it up, and the allocation cannot fail because the system is out of memory. So that's referring to this example C right here. We will look at this in the text editor. Okay. It says, note, static variables must be initialized to a value which can be computed at compile time. You cannot, for example, initialize a static variable based on the user's input at runtime. You can initialize it to a sensible default value and modify it at runtime instead. I might show an example of exactly what it's talking about, depending on how long this video goes. So this is the example that it's talking about, and let's go ahead and jump over into the text editor and break this down. Okay, so here we are in the text editor, and this is basically the same exact program that we did previously using alloc to allocate this buffer here. Now, the only real difference is that we're allocating this statically. Okay, so there's no other major difference other than this is a static allocation, and as it says, a static allocation cannot fail because your system is out of memory. If you tried to allocate this dynamically and it was out of memory, then this would fail. Okay, so that would be one advantage of allocating resources statically. But again, it says it can increase resource usage, so your RAM and disk space. So there's, like anything in programming, there's trade-offs with everything. Okay, so what's happening here is it's the same exact program. We're taking a command line argument, allocating a buffer. Only in this case, you see, we don't need a pointer because it's not pointing to a space in memory dynamically. Um, it's just a static allocation, and we're writing it to standard out. Okay, so I'm not sure if we've actually looked at the IO read function yet. So let's go ahead and um, uh, look at OSArgs, and let's look at IO read. So you can see the command line arguments provided to the program. By convention, the first member is usually the name of the program. So it takes a type of string slice. Okay. And now let's look at IO read. So that opens the command line argument because the first argument is generally the program name itself. So that would be 0. So that's why we're starting from 1 so that we can get the first command line argument. So let's look at IO read. Okay, reads up to, this is the built-in len, okay, the built-in len function of buff, so your whatever buffer, your array, slice, whichever, reads up to this amount of bytes from a handle into the given buffer, returning the number of bytes read. So here's the handle, okay, and you can see that it reads from a handle into the given buffer, okay. So we're reading from the file, okay, right here, and then we are putting it into the buffer, which we allocated here. Now here, we're passing in the buffer. Let's look at IO write. Okay, now you see it returns it as the number of bytes read. So we are type asserting on this, okay, as size, just like we did with the buff.io readline function. And you can see it can return an error. Okay, so we have to use the error assertion operator here. So let's look at IO write. Writes up to lenbuff bytes to the handle from the given buffer, returning the number of bytes written. So let's go ahead and run this program, and let's pass in our main function again, okay? So we're running the program. Now we're going to pass in the command line argument. And you can see it prints our program to the screen. So this is obviously under 64 kibibytes. It would cut off at 64 kibibytes because that's the size of the buffer that we allocated. So that is static. That is static allocation. If you're coming from C, you're going to be familiar with a lot of this, and really it would just be kind of getting used to the syntax more than anything. So let's go ahead and move on to the next example, which is going to be thinking in terms of ownership. Okay, thinking in terms of ownership. Hare uses manual memory management, which means that you, the programmer, are responsible for planning for and allocating the memory your program uses. Some functions in the standard library and elsewhere have consequences for memory management that you should be aware of. These are addressed in the documentation for these functions using standardized language of ownership, transfers and assumption of ownership, and borrowing resources. Examine the documentation for functions in this sample code with commands like haredoc io_drain. This function allocates a buffer to store the results into and returns that buffer to the caller, you, who assumes ownership over the object. You are responsible for destroying this object when you are done with it, freeing resources like memory to be used elsewhere. So you can see we're calling io_drain here, and it allocates a buffer that we take ownership over. So let's go ahead and look that up, and you can see the caller must free the return value. Okay. Many functions borrow resources to make use of them without taking responsibility for them. So strings from UTF-8 is an example of this, as we can learn from its documentation. So let's look up from UTF-8. You can see the return value is borrowed from the input. Okay, so that would be right here. Okay, so what this means is that we're just borrowing the input buffer. What that means is we're not responsible for freeing it. So if it's coming from IO drain, that's where we have to free this resource. Okay, so it says strings from UTF-8 is an example of this, as we can learn from its documentation. The return value, which is a string, does not need to be and should not be freed, and will become invalid when the buffer it's borrowed from is freed. So you see, this is where we take responsibility for this buffer. Okay, we're passing it in to strings from UTF-8, but we're only borrowing it. We're not taking ownership of it here. So we only have to free, you can see defer free buffer. Once this is freed, whatever is borrowing it is also going to be cleaned up. So it is important to read the documentation for the functions you use to understand the ownership semantics they require, and to plan for this in your program. The standard library is extensively documented, and HareDoc makes it easy to access this information. And that's one thing I would really like to point out about Hare that I enjoy about it, is how great the documentation is, right? It's really, again, if we jump back over here, you see it's really concise. You can work from the command line, which if you're using Linux and BSD, you're probably familiar with. I prefer working mostly from the command line. Now, of course, you could look up this documentation online if you would like also. It's on the website. If you go to the documentation, you can find the standard library documentation. And that's a good way to kind of get an overview of the modules, and if you'd like to look online also. But the documentation is great, and you can see it tells us explicitly, if we are taking ownership or if we are borrowing. So we have to be aware of the semantics of the language and plan accordingly, and that's why it's important to use HareDoc very liberally. You should be using it for every function that you're calling. Now, in one of my previous videos, the thing about Hare is how simple it is, and when I said it's possible for a single programmer to keep the entire language in their head, I was not referring to all of the standard library functions. I'm talking about the core language, right? The core semantics, the operation of the language. That is possible for a single programmer to eventually just put into memory. It's a very simple language. But you are going to be having to use HareDoc to look up all of your functions that you call. And that's one thing that I really appreciate about Hare, is that it really encourages good programming practices. And again, if you read through some of the blogs in one of my earlier videos, I think it was the language overview, I talked about, the way I put it, sort of the values that they're trying to instill in the programmers that use Hare. Okay, and so in my opinion, it encourages good programming practices because it's really easy to look up your functions, and you should be anyways. Okay, you do not want to be putting the error assertion operator everywhere just because. Okay, that's not the way Hare was designed. Hare was designed to eliminate a lot of these edge cases and undefined behavior and errors from C. Okay, and so you should be using the language properly, and what that means is that you're going to have to use the HareDoc tool to look up your functions. And I know that might seem a little verbose at first, but it's no different than any other language. If you were developing in C or C++, you'd have to be looking up man pages or CPP-ref. You'd have to be looking up all of your functions regardless. So it's not like it's overly restrictive in that sense. So that is thinking in terms of ownership, and it's important that you understand these ownership and borrowing semantics so that you can free your resources and deal with your resources appropriately. Okay, now you see here it says note. Let's read this last little bit here. Note, we use terms like borrow and ownership to reason about memory, but this is not enforced at the language level. The compiler does not prevent double free or use after free bugs. Hare does have other safety features, however, which will be addressed later on. So you can see that Hare is not a quote-unquote perfectly safe language or a quote-unquote memory safe language. Obviously, you have manual memory management. Now, to my knowledge, there is some static analysis built into the compiler itself. So let's go ahead and look at an example of that. Let's look at a use after free, and let's look at a double free and see how the compiler handles that. You're allowed to do it semantically in your code, but let's see what happens when you actually do have a use after free or a double free. Okay, so here is just a little snippet of code from a previous example, and you can see we're just calling alloc to allocate a resource dynamically, and here's our free. Here's where we're freeing this. Well, let's look and see what happens when we have a double free. Okay, so we're going to free this object twice. Let's go ahead and run this program. And you can see it aborts, and it detects right here, see, double free. So it does detect the double free, see, already freed pointer. So this is from the runtime module. This is from the runtime malloc module function. And it says, see, double free. So it detects the double free. So let's look at a use after free. So let's go ahead and remove this, and we'll dereference our pointer, and we'll just assign a new value. Okay? So this would be an example of a use after free. Let me clear my screen. And you can see it does detect it. Use after free. You can see that right here. So it does detect the use after free. Okay? So Hare is not a perfectly safe language. Okay? Which is fine with me. I come from the C world. I'm not writing production level code for, say, like medical equipment. So it's not something I have to worry about. But I also think that every systems developer, anyone who's learning about systems level programming, especially in Unix, I'm not familiar at all with Windows. I know Mac is basically BSD under the hood. But any developer should, I think, my opinion is that you should become you should become comfortable managing your own memory regardless. I come from C, so it's not a big deal for me. Now, I'm not an expert in manual memory management. There's a lot that I'm still learning, especially with like pools and arenas and things like that. But it doesn't bother me at all. I love the language. I think programming should be fun. Now, in a previous video, I said I hope that the linear types land for manual memory management. Well, I've kind of reassessed that, to be honest, because I don't know. I like the language how it is. Now look, if Drew and the rest of the design team wants to put linear types in, then that's fine. If they don't, I'm also fine with that. Not that I really have any say in the matter. But I'm just saying, some people, especially nowadays, are really kind of, against these languages that allow you to manage memory on your own. And in certain contexts, I can kind of get on board with that a little bit, right? Like if you're writing extremely critical code, right? again, for like hospital equipment or things like that. You don't want null pointer dereferences and use after freeze and things like that. And if we can implement some more safety features, I'm all for that. But again, if you read through the blog posts, you know, Hare is not out to conquer the world. It's a systems level language. So it gives the programmer control over things just like C does. Okay, and again, on your arrays, you can turn off bounds checking, for example. Okay, so it's a systems level language designed to write low level code. And it's fun. You know, I enjoy writing code because it's fun. I enjoy programming in Hare because it's fun. For me personally, again, I'm not writing production level code. I don't want to take all the fun out of programming. I enjoy managing my own memory. For me, it's kind of like a puzzle to solve, you know? Um, so I enjoy it. Um, so that is an example of a use after free and a double free. But of course, right, any good C programmer knows that you'll never get a use after free or a double free if you never free your memory. Okay? That was a joke. Okay, if any of the Rust crowd is watching. Um, anyways, so that is the section on memory. I hope you found this helpful, and please stick around for the update on my book if you would like, and if not, that's okay. You can join us in the next video, which is going to be error handling, I believe. Let's go ahead and look at that real quick. Yes, so the next video, we're going to get into handling errors, and this is where we're really kind of writing comprehensive programs now instead of using the error assertion operator everywhere. So thank you so much if you made it this far, and I really appreciate you. I appreciate all my subscribers. I have no desire to turn this channel into anything other than just very niche kind of programming content. I have no desire to create like flashy thumbnails and clickbait type content. So it's just really going to be what you've seen so far is pretty much what my channel is always going to be. So thank you so much, and let me go ahead and give you a brief update on the book that I'm writing. Okay, so I wanted to give a brief update on the book that I'm writing called Programming in Hare. I apologize for the brightness. I personally like to read PDF documents in this format. I do have a dark mode on this, but it's not a real dark mode. In any case, so this is just a PDF that I have put together so far. I'm using Hare version 25.2. The name of the book is called Programming in Hare, an Introduction. And this is really kind of targeted at kind of beginner and intermediate level programmers. This is definitely not necessarily meant for experienced developers. And this is just the PDF that I have built. If something is in here, it's generally finished. There are some things I would like to kind of add to it a little bit. I have the license is a Creative Commons license, so it's open. You are free to share this. It's non-commercial, so but you are free to redistribute this, build upon it, anything like that. I have all of the source code here on my repository, which I will show you. And actually, I'm missing a tilde right here, so that this link doesn't actually work. I have to replace that tilde. It's built with Pandoc. The main text font that I'm using is Free Sans, and the code font that I'm using is Free Mono, and both of these are from the GNU Free Fonts project. So if I come back up to the table of contents, this is the latest section that I added is arrays and slices, and I just get into the basics of declaring an array, and I try and break every little part down, right? Array initializer syntax, and some of the, you might be familiar with some of this from watching these videos. So avoiding magic numbers. I show you how to use def to put a buffer size into an array, the built-in len function. I cover bounds checking, and you can see I have just simple code examples, right? So like I'm saying, this is meant for like beginner and sort of intermediate level developers. Um, I'm trying to make an introductory book to Hare, right? So that people have something to go to, and they can start learning this language, because I think it is an absolutely great language, and it's 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 a great, I think, first language to learn. And I'm not trying to say that it's like, when I say that, I'm not saying that you have to eventually progress beyond Hare, right? Because it is a systems level language. It'd be no different like if you said C is a great first language to learn, right? You could spend your whole career programming in C and be perfectly fine. But the language itself is very readable. Okay, it's extremely readable. In my opinion, it's much more readable than C, um, and has some extra safety features on top of it, um, to eliminate undefined behavior and all of these edge cases. Generally, what you'll find in Hare is there's generally kind of only one way to do something. Of course, now programming is, I can't remember the famous programmer who said it, but they were asked, is programming an art or a science? And he said it's a craft. Okay. Um, and I would agree with that, right? There's multiple ways to solve problems generally. Um, I forgot where I was kind of going with that. So then I go into slices, declaring slices, right? And you can see this is just, really simple code. Okay, so here's the appendix. This is obviously not done. But if I go over into my repo for it, it's hosted on SourceHut. Now, I don't really want to give this out. I did put this in a link to, um, in the comment section, but it's not done. It's nowhere near being finished. So I do have a website for it, but my main focus is on the PDF document. It's going to be PDF and EPUB, and that way you can have it. You can have it on your system, and or on your phone, whatever, and you don't have to access it online. Okay, it started as, the way that this book started was basically documentation for me learning the language. It was like self-documentation. I'm like, you know what? I'm just going to put this into a more formalized um, format. So here's the book, here's the website. If you go to the book directory, here's the PDF you can download. Um, and here it's written in Markdown. I build it with Pandoc. So if something's like right here like this, it's generally finished. But as you can see, I have a lot of other stuff that you know, I'm working on. So here's, if expressions, and you can see this is just very simple code, right? I try to explain, right, the basics of the language in a way that's not overwhelming. I keep the examples relatively short. Now, that's not to say we won't get into more complicated code towards the end of the book. Once your knowledge of the language is built up and you're comfortable with the syntax and using all of these features, then I'm going to put some programs in the back of the book, command line programs, things like that, where we're actually building like file utilities and maybe even um, some like the GNU core utils, maybe like we'll build cat or, ls or something like that. But you can see I have a lot more that I'm working on that's not actually in the PDF part of the book. Um, and you can see I just pushed this repo about a week ago, doing some refactoring. I have been extremely busy lately, um, but I was hoping to try and get this out before Christmas. I don't think that that is going to happen at all. Plus, I do want to add a couple more, uh, other parts to it. I want to add some parts on debugging with GDB, and I just added this part here. You can see I just have the title, An Introduction to Context-Free Grammars, and the Hare language spec. Now this is going to be, very introductory type material, but I want to put stuff like this in here at an introductory level right towards the back of the book. And this would be necessary, for example, to understand the Hare language spec. Okay, that's what an experienced developer would go and look at for Hare, for example, would be the language spec. Well, that's what I'm working off of. So I've had to learn, EBNF, which is extended Bacchus Noer form, to understand the grammar of the language, to understand how it's constructed, to understand what you can do with it. So that's basically what the book is being built out of, is the language spec. So here's like the introductory part for tagged unions, and you can see if you're not, familiar with tagged unions, I just I break things down hopefully as simply as possible. Again, when I'm almost done with it, I'm going to get some feedback on the Hare user mailing list. And now, one person asked if they could contribute to it. It's not that I'm against contributions. It's just that I have a specific vision with this and kind of a target audience and a way I like it organized. And what it comes from, okay, look, what this comes from is from me being a relatively inexperienced programmer and trying to learn Hare, okay, and kind of laying things out um, the way I wish that they would have been laid out for me when I started understanding the language. So I hope that that doesn't, come across the wrong way, but I probably won't accept any contributions just because I have a specific vision for the book and a target audience in a way that it's organized that I feel would benefit someone who's generally, who might have a little bit of experience programming in C, but who wants to learn Hare. Basically, this book is targeted at people who have taken like an introductory programming course and they know basics of like looping and functions and variables and and things of that nature. So um, so that's basically an update on the book, and I am working on it when I do have time. So that is it for now. Um, Thank you so much for watching, and I really hope you find this whole series helpful. And please stay tuned for the next series in the Hare programming language tutorial, which will cover error handling. So thank you so much, and have a nice day.